This is problem 4-59 on page 146. The friction at sleeve A can provide a maximum resisting moment of 125 newton meters. Sounds familiar, doesn't it? Yeah. About the x-axis. Determine the largest magnitude of force F that can be applied to the bracket so that the bracket will not turn. Now notice the 60, 60, and 45 degree angles are with respect to lines that are parallel to the coordinate system. You notice that? So they've given us essentially coordinate angles. And so what I'm going to do is sketch, I guess I'll sketch the problem again on the board so that we can talk about it. So here's our rod. And then the collar, something like that. And the arm coming off of the collar generally goes along the y-axis. Going along the y-axis, I'll make that a dotted line so we can still work with it. And then it bends off and up. Kind of odd, but good enough. And then there's some kind of a shaft or something at the top. I don't know what it is. It doesn't really matter. But the point, and actually it looks like that, I shouldn't have drawn it quite this way, because this whole arm is supposed to be in the XY plane. So let me change this just a bit. Let's make it look more like it remained in the XY plane. There, that'll be better. Okay. And so the force F is applied to the top of this point where the geometry is 300 millimeters. Really that's out to here. So along the y direction we've got 0.3 meters. One of the things I like to do is immediately convert units when I'm given them if I think that it'll be more convenient. So 300 millimeters, just move the decimal place three times to the left, you got 0.3 meters. Same thing on the other dimensions. For example, the dimension from here to the y-axis is 0.15 meters, or in other words, 150 millimeters. And then up from the xy plane to the point of application of the force is 100 millimeters, or 0.1 meters. Okay? Now, I did go ahead and draw these. I don't know why I drew so much in my solution. I just decided that it would be beneficial. Maybe I didn't quite feel like solving the problem yet. Sometimes I'll do that. I'll sketch the system when I don't really quite feel like solving it yet. Give me something to do. But anyway, so here's F, and then we've got an angle of 60 degrees down to this axis parallel to the y-axis. We've got an angle of 45 degrees up to the z-axis, and then an angle over to a line parallel to the x-axis is another 60 degrees. One thing you should always do, and I remember why I drew this now, and I wanted to mention to you guys, one thing you should always do is make sure you understand exactly what's being given to you in the problem. If you start working the problem and you realize, oh, I misunderstood one of these angles here, then you may have serious problems and have to go back and change things quite a lot. So anyway, the first thing I did is I decided to write down F as a vector, because my goal is to take obviously the cross product of R and F. I got to decide what R is exactly, so I thought, well, I'll just go ahead and write down F immediately. So help me out with F. If I knew the magnitude F, which is of course what I'm looking for, then I could type, or I could plug it in, but I don't. F is what I'm looking for. All I want then is something that gives me the unit vector along the direction of F. So along the x-axis, how would I calculate the component of a unit vector in the direction of F along the x-axis? In other words, along this axis right here. What would I do? What's that?
Wouldn't it be cosine?
Cosine, good. Of
0.15.
Of what?
It'd be cosine 0.15 meters. Or no, the angle. I know 0.15 is involved, but I know it's cosine.
Actually, the 0.15 won't be involved. You're thinking of using all of these dimensions, but that would give you something like that.
Oh, okay.
You see? That's what you're thinking. I'm interested in F.
Okay.
Cosine of 60.
Cosine of 60, exactly. Does everybody see why it's cosine of 60? It's because what I'm doing is projecting this direction onto this line. Do you see the right triangle there? It's odd, it's at a sort of an angle. So imagine my hand is parallel to X and then I rotate it down a bit. That 60-degree angle is in that plane. Does that make sense?
If you were given dimensions, could you use the dot product somehow? 'Cause
If we were given dimensions, I would go back and do what he was suggesting here with the inverse cosines to get angle. Or better yet, calculate the length of this vector and then take this, well, for X I would take 0.15, which is what he was trying to do, over the length of the vector.
yeah, like I heard projection, and I know from memory that that's just what the dot product does, but whenever I think of projection, I think of doing exactly what you're doing. So I'm trying to think of a way that you can use dot product here, but I don't think you can.
Don't think it would be useful to us. Go ahead. Yeah.
Would cosine need to be negative since it's going in the negative x
Good
direction?
question. That's what I was about to ask you. You're right. Notice that F points generally back this way. It has a negative component in the X direction, not a positive. Okay? So you're right. I need to attach a negative sign. Good catch. And that's in the I direction. Okay? All right, so help me out with the next component in the J direction. What should I write for that? Well, J is this way. So what would I do there?
Cosine 60
Cosine 60. Plus or minus?
plus.
Good. Last one?
J. Oh, never mind.
It'd be K, because.
Well, no, I didn't see you wrote J up there yet.
Oh, I see. Gotcha. So the vertical component, the Z component.
Cosine 45.
Cosine 45.
That's it. I've written F as a vector. I've got the unit vector here, and all I gotta do is multiply by F. Okay? You can check that this is a unit vector by calculating the magnitude of it. Just take the sum of the squares. You should get 1. Okay? All right. What about the position vector? I'm going to go from A to B. What do I mean by that? Well, if you look at the problem statement, they've given us the origin as A, the point of application of the force F as B, and in fact, whoever it was that wanted to go from here to here, we're going to do it now. Except, wait a second, I'm not really interested in a unit vector. I'm interested in a position vector from A to B. So help me write this down. Along the x-axis, how much length do I have?
0.1 meters. Oh, no.
Negative.
It's 0.15.
Negative.
Negative 0.15, isn't it? Good. Okay. In the y direction? 0.3. Right. Plus 0.1. Okay. These have units of meters. Obviously, I'm going to have newtons here, but the newtons will be on F.
Yeah.
Okay. Now, to calculate the moment of F about this line, I'm going to start by calculating the total moment, M, equals RAB cross F. Be really careful. You always have to take the position vector crossed with a force, not the other way around. If you go the other way around, you'll get the negative of the correct answer. Okay? So, all I need to do then is take the cross product of negative 0.15i plus 0.3j plus 0.1k. I'll leave the units off for the time being, with negative cosine 60i plus cosine 60j plus cosine 45k. Hopefully that's good enough on the video. And of course, the units here will be meters, the units here will be newtons. So we'll end up with meters times newtons or newtons times meters, either way. Usually we'd use newton meters for torque. Okay? Now how do we perform this cross product? The easy way is to calculate the determinant of this matrix. Notice I'm not using the triple scalar product, although we could do that here. What I decided to do is go ahead and take the complete cross product and show you. I'll try to draw the moment, okay, of this force at A, and then show you how we project it onto the x-axis. Okay, so we're going to take the determinant of R cross F. So R is negative 0.15, J 0.3, K 0.1. These are all meters. F, negative cosine 60 degrees, cosine 60 degrees, and then finally for the K component, cosine 45 degrees. You guys remember how to take the determinant of the matrix in order to calculate the dot product? You probably have to look back at your notes until you get this memorized, okay?
So you do 0.1.
Cover one, good. Right. So if we want the I component, cover up the first column, first row. And let's see, let's just put I in there first. And then 0.3 cos 45 minus 0.1 cos 60. Cos 45 minus 0.1 cos 60. Now what I usually do, because it takes so much length, is I will typically drop down to the next line and write negative j. Remember, it's positive, negative, positive. Remember that? That's the order, or that's the pattern. And then for the j component, I'll cross off the first row, middle column, and write minus 0.15 times cosine 45 degrees. Now this negative sign first came from here, but this negative sign is because it's the difference, right? So times 0.1 times negative cos 60 degrees. So negative times negative will be positive, but remember this negative came from the fact that it's the second term being subtracted from the first. Then finally, plus k times, well, let's see, negative 0.15 cos 60 degrees minus 0.3 times a negative cos 60 degrees. Okay? So hopefully you can see the pattern. When I plugged all this into my calculator, I got about 0.1621i plus 0.1061j plus 0.1811k. Now I forgot something here. I forgot that from here to here I dropped the f, right? I needed the magnitude of the vector and I forgot to write that down. So I need really f times this. So this whole thing is multiplied by f. What that means really is I just need to tack on a times f here. By the way, well, I won't say that, it doesn't matter. Okay. And the units, of course, will be Newton meters. Now, let's look at this and see generally in what direction, make sure I've got all my signs right. Let's see generally in, oh, you know what? I wrote plus for the j component. I wonder if I've got this backwards. I wonder if this should be negative. Would you guys mind to check? Because we need 0.1 times cos 60 degrees, that'll be positive, minus 0.15 cos 45. Do you get a positive or a negative number there? I may have made a mistake in my solution. So the j component, did it come out, does this term come out positive or negative?
Just the inside parentheses.
Comes out, yes, just inside the parentheses.
No, I don't have it yet.
Oh, sorry, okay.
It's a negative inside.
It's negative, okay, so then it'd be negative times negative is positive, okay, all right. I just wanted to double check, because what I wrote here was plus j, and I should have written minus j.
I got a different number than you got though.
What did you get?
0.056.
Anyone else agree?
That's what I got.
Yeah,
That's
you
what I
gave
got.
0.056.
Okay, so apparently I kept my signs right, but made a mistake punching buttons. 0.096, you said?
5.6.
5.6, okay. It turns out it won't matter. You know why? Because all we really want is the component along the x-axis. So really, the only moment we're interested in is this. There's that. So that's why it didn't appear in my final solution. In other words, the unit vector along the axis that we're interested in is simply I. Right? That's the axis we're interested in, which makes life easy because now if we take the dot product of m and I to get the scalar magnitude of the moment about that axis, it's simply 0.1621 f, right? And that's it. So this is the moment that has to be at most 125 Newton meters. And so all we have to do is solve for F. F is equal to 125 divided by 0.1621. When you do that, you'll find it's about 771.1 newtons. Notice that this term over here is Newton meters. F has units of newtons by itself, and so this thing here must be simply meters. Okay? That's not technically correct, but it's close enough because I don't know that you could really interpret this as length. Anyway, so 771 or so newtons would be the maximum force you could apply before the arm would start rotating about the x-axis. Okay? Any questions? Comments? So what did we just do here? Well, we calculated the total moment. We left it as a vector so that when we took the dot product with the axis we were interested in, we would get just the moment about that axis. Okay. No questions? You guys seem to be, you kind of have that deer in the headlights look that I'm used to seeing. Go ahead.
So what really is your determinant? What isn't?
What is that? That's the cross product of the two vectors.
Okay.
That's what it really is.
It seems really similar to a unit vector for some reason.
This, let's calculate the magnitude of it. I don't think it is. I don't think it's going to be equal to a unit vector. But it does give us the direction and relative magnitudes of the moment in all three directions. So somebody calculate the magnitude of this, trying to 0.1621, 0.056, and 0.1811. I don't think there's any way you can get one out of that.
What is that?
Any other questions? All right. Well, I guess I'll show off the video then.